So this is our third problem on beam, steel beam, double section beam. In this math, you can see from the title that is the section will be non-compact one. So previously, we had a section of both compact one and non-compact one. This one is a non-compact one too. So for the first criteria, we have an unbraced length of 0 feet, and for the second case we have an armrest length of 10 feet. So in the first case the beam is fully braced. In the second case the unbraced length of beam is 10 feet. So for the first case, let's for the first case, we're going to solve that. We're going to first of all check that if our value is within the compact region, this compact region. And for the compact region, you need to check the slenderness ratio of your beam. So we'll find out lambda. That's for one for your what we can say flange, and we'll find lambda for wave, and we'll check that value with our maximum value, that is 65 root over fy for that one is for flange, and that is the highest limit of plastic moment. So for that, we'll go to the AIC manual, and from that manual we'll find out the lambda f and lambda w, and the section is w10 12. I already have marked that one is W10 12. So from there you can see that this criteria is for compact section criteria. Your BF by 2TF value is 9.43. You can see it from here, and your H by TW value is 46.6. So these two values are important. So first of all, BF over 2TF value, and from this you can get a value of that was already told, that is 9.43 if I'm not wrong. That is 9.43, isn't it? I have forgot that. Yeah, that is 9.43. And the highest value of slenderness of flange, that is root over 65 root over fy. So we'll find that value also, and from that you can say the section is uh, the section is going to have a plastic limit or not. And here you have ultimate value, that is 65 root over fy, and this value is equals to 9.15. So this value is less than lambda f, so you need not to check this criteria. So the section is already a non-compact one. So from here you can say that the section is non-compact. So for the first criteria, the section is non-compact. So the moment is in this region, though it is not already proved that the value is within this region or not. So for that you need to find out the value of lambda rf. So from where you can find out the lambda RF value. So lambda RF value is 1 multiplied by the root over value of E over Fy, and the value is lambda RF value is 1 multiplied by the value of E over Fy. Here the E value is 29,000 KSI and the Fy value is 50. So from there you can find out the value of lambda RF, and the lambda RF value is 24. So from here you can see that your lambda value, which is 9.43, is greater than this one, which is lambda pf, the slenderness ratio of flange at plastic limit, and is less than the slenderness ratio of flange at this limit. There is a name for that, I have forgot that. However, so we can now say that the equation that you will use for finding out the moment, that would be this. So this formula you will use, since the flange is non-compact one and you are lying in this region. So the equation you're getting is mn is equals to mp subtracted by mp minus zero point 0.7 fy sx multiplied by lambda minus lambda pf over lambda rf minus lambda pf. So from here you can find out the mp value. You need to know this value, but this value I haven't calculated it yet. So I need to calculate this one to find out the nominal moment in this region. So the mp value is equals to fy zx. The zx value you will get from the AIC manual. Well, the zx value is this, and the value is 12.6. So this one is your zx value. We'll just multiply zx value with fy. Fy is 50, and zx value is 12.6. From here, you can find out the value of mp. The value would be 630 kip inch. Well, now the thing is that you need to find out the value of mn uh, in this region, non-compact region. So your mp value is 630.7, fy value is 50. Your sx value is section modulus. You will find it from the AIC manual, and you will get a value of 10.9. Your lambda value is the lambda value what you have just calculated, that the value is 9.43, and lambda pf value is this one. This one is lambda pf, which is 9.15. Lambda rf value is this one, which is 24, and lambda pf value is 9.15. So you have got a moment of 625 kip inch. If you convert it to kip feet, you will get a value of 52.1 kip feet. So this is the math for the first criteria when you have a fully braced beam. So we'll go to the next criteria, that is you have an unbraced length of 10 feet. For that, we'll go over here. So the thing is that we'll find out LP value. This will find this LP value, and we'll find this LR value, and we have equations to find them, and we'll check the region we lie. If we lie in this region, we have a formula for that. If we lie in this region, we have a formula for that. If we lie in this region, we have a formula for that to find out the moment. So the thing is that you got to find out the zone you are lying on. So let's find out the LP value. For LP value, we have a formula, that is 1.76 Ry multiplied by E over Fy. Here Ry is radius of gyration around y-axis. You will find that from the AIC manual, and the value is 0.785, and E value is 29,000 KSI, and Fy value is 50. From there you'll find a LB value of 33.3 inch, and if you convert it to feet you'll get a value of 2.77 feet. Now you need to find out the value of LR. For LR you have a really big formula that's humongous. The formula is 1.95. We used this equation earlier, so I hope that you are already familiar with this. Zero point 0.7 Fy root over J C over Sx H naught root over 1 plus root over 1 plus 6.76 over zero point 0.7 Fy Sx H naught over E J C squared. So your RTS value is radius of fillet, and the value is 0.983. You see that from the AC manual. I'll show you. Your J value, you will get a value of 0.0547, and C value is your CV value that is already given, that is 1. And your SX, this is actually SX, this is actually section modulus around x-axis. H naught is the central distance, and uh, this Fy, you know this, all the things, yeah, you just know that J value is your rotational constant. So you can find these values from here. So this is your Sx value, which is 53.8, sorry, 10.9. Sorry, this one is for W1012. So sorry, yeah, this is the section. Sorry, and your Ry value is this one is for your Ry value, which is 0.785. We'll use this, and you need RTS value. You'll get RTS value where this is your RTS value. Your RTS value is 0.983, and you need your J value. This is your J value, which is 9.66. It should be 9.66, isn't it? Sorry, 0.0547. I have missed the column. And you need H naught value. Your H naught value is 9.66. Yeah. And you need S value. Your S value is for Sx. So S value is 10.9, which is this. So you can get all the uh, parameters from here. You will just put them in this equation, and you will get a LR value of 96.6 inch. And if you convert it to feet, it will be 8.05 feet. And your LV value is 10 feet, if I'm not wrong. Yeah, it was 10 feet. So you can see that your LV value is greater than LP, and it is also greater than LR2. This value, this one is greater than LR2. So it is greater than LP. Your LV value is greater than LR2. So you are lying in this region. So for that region, you have an equation to find the moment, and the equation is Mn Mn is equals to critical stress multiplied by Sx. what we have already used, that is 10.9, but you don't know the value of FCR. So how can you find out the value of FCR? For FCR, you have an equation that is CB, what is already given, that is 1, CB multiplied by pi square E over LB, unrest length, over radius of fillet, my, I guess it's called radius of fillet, squared root over 1 plus 0.078 multiplied by JC over S H naught LB over RTS. So you know all the parameters JC is H naught LB RTS. Your J value is 0. 0. I'm writing it that right over here. J value is from the AIC manual 0.0547. Your LB value is 10 feet. You need to convert that to inch, so that will be 10 multiplied by 12. You have a C value is 1. You have an H naught value of 9.66 inch, and you have a S value that is 10.9. That one is also inch. That was 3 inch. So this value is in inch to the power 4. What do you need else? You need a value of RTS. Your RTS value is 0.983. So now you know all the parameters. Just plug in the values and you'll get a value of FCR 24.3 K. So if you know the value of FCR, then you can find out the moment in this elastic region, that is laterally torsional buckling will occur in this region. Your FCR value is 24.3 and you have an SX value is 10.9. From here you can find the value of Mn, that is 265.1 cube inch or 22.1 cube feet, and your factored moment will be is the factor, sorry, if you want to just reduce that reduction factor, which is 0.9, 22.1, and that would be 19.9 cube feet. So this is the answer of this math. So this is the third type of math, and this is the last type of math from beam. We'll solve another one problem on beam, uh, considering the serviceability condition.